And human beings react to visual representations. Seeing it makes your brain go off in all sorts of ways. You can say, oh, I mean, at the very least, even a child could say, this one's bigger, this one's smaller, this one has more fine structure, this has less. Or you could say, oh my God, do you see a hexagon in there? Do you think it has six-fold symmetry? What does that mean?
Well, you could also think about using physics to create art, right? It's basically the same thing regarding, for instance, diffraction. X-ray or electron diffraction, it is all based on a physical mechanism, right? And this can be put into an equation, which has a lot to do with symmetry.
Physics rests on symmetry and symmetry breaking. And if I said, if I told you a sphere was completely symmetrical, you'd nod your head. And if I told you a striped sphere, like a beach ball, is less symmetric than a plain red sphere, you'd also nod your head. And so these notions of symmetry, I think, are inherent in us. And in physics, it makes use of very subtle symmetries. There are many, many other symmetries, not merely visual symmetries, that actually lead to very beautiful and exciting physics. I'm sure you've learned about the hydrogen atom, for example, and this was one of the first major successes of quantum mechanics, right? But if you look at all the ways in which electrons go around the nucleus of the hydrogen atom, it's extremely beautiful, right? It shows you these shapes that have all different symmetries. It shows you these colors which indicate where an electron is more likely to be found and where it's less likely to be found. And that comes straight out of quantum mechanics. And I think that is beautiful.
Mathematical equations, which physics is one core entity, right? Those equations are precise, but difficult to understand. To really understand what these equations imply, typically you have to visualize it.
There's sort of two bits to it, right? There's what we actually see with instruments, and then there's what we visualize by doing computer simulations. And both of them, and sometimes the two intersect because you use what you have and then you put it into a computer and you get something out.
And I'm pretty sure you have seen The Matrix also, right? Where there are some folks who see just numbers. And I belong to those who just see numbers. But others might see really a pattern behind there. And that's the difference between computers and people. It's just a 2D array of numbers, but how we actually interpret it is by visualization. So we assign to each number a color or a gray scale. And same thing, you can use those to input it, and then you get something out, which is really at the crossing between art and physics. And if you then change a bit, color space, for instance, you end up with pretty beautiful images. Like, for instance, I generated a couple of years ago, like a Christmas tree almost, just out of a diffraction pattern that you can, for instance, have very sharp and structured images, and they transform into, let's say, more liquid-like aspects. And this you can simulate, but also experimentally do.
Something called scanning probe microscopy has really made this come alive. In real space, we can look at the level of individual atoms, and we can see where there are steps and where there are valleys. That's sort of a zeroth order thing. But we can also see where the electrons congregate and where they're not. We can look at the wave nature of electrons. There's a famous, quite old picture of what's called the quantum corral. They made a little circle of atoms, and they see the wave nature of the electron they deposit in the middle. So it's quite exciting. Scanning probe microscopy, for instance, can show you the way magnetizations point. So you have a thin film of a perfectly uninteresting material, right? It's just magnetic. And then you tickle it with magnetic fields and it breaks up into domains. And those domains may do something quite remarkable. And those are very beautiful. Some of the exciting things we're doing just now is we have what's called a domain wall in a nanowire. So you just have a wire of a magnetic material. And on the left-hand side of the domain wall, say the magnetization is pointing up, and on the right-hand side, it's pointing down. And so using little bursts of sound, we've made that domain wall walk across the thing. So we haven't used a magnetic field, we just use little bursts of sound. So that's a very cute video, I think. The shapes of those domains are so varied, so variable. You can get so many different shapes.
Science, math, etc. All those things are very abstract and intimidating in the beginning. And I can assure you, it will never stop being intimidating. Even professionals have problems. And this is what science is about, right? Identifying problems and cutting to the chase and identifying, something which we can solve. Like, I'm not an artist, but you can say like, well, that's what I do. I mean, obviously it's kind of a lie, but it's one product out there, right? So you can actually nicely share this also with others.
Now that's nano.